Okay, thank you very much. It was a beautiful talk, and let's have a applause. And yeah, the floor is now open for questions if you have. I mean, I have myself a lot of questions, but let me first open it with others. So, um, uh, Mariam, you can, yes, go ahead.
Sorry, first of all, thank you, Dr. Stahl. That was a very excellent presentation in detail of manufacturing design and the detail of functioning of the system. Sorry, this computer is registered under my daughter's Maria. That's why. But I have a lot of questions. Actually, recently I have studied the work done by Stephen Hawking the past few years. There is a lot of questions which is relevant to the presentation of today. I start with the first one, and whenever I get time, I'm going to go a bit further if possible. Okay, the first question that I'm asking is that how far did you go back to find the position of the age of the Big Bang exactly, if possible, and of course whether that point of Big Bang was the point of collapsing of another period of time, according to Russian scientists. Thank you.
So first thing I want to say is that I'm an optical engineer, not an astrophysicist. So my answers may or may not be completely technically correct, but it's my understanding that there is no point of origin that we can find for the Big Bang. We cannot reverse the clock, if you will, to find a single origin starting point for the Big Bang, and that there is no center, if you will. The other thing is that we've gone back with Kobe and MAP into the time of a few hundred million years or a few 100,000 years after the Big Bang with the cosmic microwave background. So I think the edge of what we can see to is to the cosmic microwave background.
Okay.
Yeah, that's exactly true. I mean, this cosmic microwave background plays like a firewall between us and the anything which happens before that, and that CMB background radiation happened 380,000 years after the Big Bang. So we are so far limited within that distance. Okay, Mr. Hossein, if I follow correctly, you are the second one.
Yeah. So I have a question. First of all, thank you very much. It was an amazing, like you covered everything from the Big Bang to life. But my question was a couple of weeks ago, I heard something, there's a news that they after the first image of James Webb was published, they and it was very, very exciting, and everybody was like, anybody who was interested in this, they said that they have to change some parameters, or they found something that it requires a correction to something. And I was like wondering what it was and how much it affects the data. And I'm not an engineer, I'm not a physicist, and I was just interested to know what was going on, and if it's true or not.
Yeah, so right, we're still in the process of fully calibrating the instrumentation, and it appears that the sensitivity of some of the detectors as a function of wavelength was not fully correct. But it's also my understanding, I think I read something. So let me sort of back up, is that I get a daily email from NASA of everything I'm supposed to know as a NASA person. And so in my news feed sometime this week, I remember, I read a little a blurb that they think that this calibration effect is only going to change results by a couple percent. So it's a fairly minor fairly minor impact, but it's a product of the fact that everybody wanted to see the results. And so, we launched on Christmas Day, and we started seeing engineering data, I think, in April, and we were under intense pressure to start releasing to the public. And so we started releasing data to the public in July. And because Webb is so much more sensitive, it's got more detectors and more collecting area, it's generating data at an incredible rate. And so, maybe we're getting a little bit ahead of ourselves, and as we go along, this calibration process on Hubble might have taken 6 months, but Hubble, we're taking on with Webb. And so let me back up for a minute. Is that I said the collecting area is 6 times bigger, right? So Webb collects 6 times more data than Webb, but Hubble only gets data when it's in the shade, so it's only getting data half the time, whereas Webb is so far out that it gets data all the time. So it's really collecting an order of magnitude more data. And so Webb produces in 1 month the same amount of data that Hubble would produce in almost a year. And that's important. So, whereas Hubble may have had 6 months or a year to get all of his calibrations right, we're 3 months. We're 3 months into Webb. We've got equivalent of 3 years of data that would have been generated with Hubble. And so, if they have to tweak the calibrations and go back and process the results, it's not surprising, and it's probably, as my data feed tells me, and my briefing told me, it's only a few percent of change in the results.
Thank you.
Okay, Mr. Hanachi.
Well, first, I'd like to thank you very much for the excellent explanation about this amazing creature, I can say. I have different questions, but I'd rather ask one which is probably more related to your area. Well, I can imagine that the data that is generated or received from the telescope is shared through some protocols to the users all across the world, to different institutions, universities. First of all, if you can explain about this process, how the data becomes available to different institutions, that would be amazing. And second of all, I would, well, regardless of the way the data is shared, I believe the point of focus, the physical point of focus for the telescope, is something that is decided probably by some priorities, where in the space the telescope should focus to collect data. What procedure is about that part? How the priorities? Because apparently we are thinking of some tip of the nibble in a football court. So how we decide where we put that?
So what it is that before we even ever launched Webb, we put out a call for proposals, and we said, you astronomers, do you have an idea of what you want to study with Webb? Send our proposals. And those proposals then were evaluated and ranked and categorized. And they were done in a double-blind method, so that they were gender neutral. Is that there was no. We also tried to strip out any kind of information about, well, this proposal is from Harvard and this proposal is from Podunk U. We try to strip out any kinds of things that might bias the reviewers, as terms of, this is a big name person, this is a big name school, and we want to select the best ideas of how to use the telescope. That the individual instrument principal investigators, the people who developed the instrument and designed and built the instrument, they have a certain amount of guaranteed time that they can study whatever they want to study. And then the rest of the telescope time is opened up to these proposals. And then the Space Telescope Institute's job is to schedule where to point the telescope in the most efficient manner to do all of these different science requests, because we don't want the telescope going from here to there, back to there. And then all of the data that gets taken gets put out into a public data. There's a public website that anybody in the world can access the data and process it. And in fact, some of the movies I showed you that was comparing Hubble with Webb was done by a art student, a graduate student in California who's an art student who pulled the data and made this animation.
All right, thank you
Okay,
very much.
thank you. Okay, so Mr. Hassan, if you have a question.
All right, so just want to start with saying thank you. Actually, I had a small role in this map satellite many years ago on the Canadian side, and it was very minor, small satellite on its own. And we had to go through many.
So before you get to your question, I'll tell a story. Is that I was giving this lecture to an SPI student group at the University of Monterrey in Mexico. And so I'm having breakfast at the hotel that morning, and this guy comes up to me and he says, "Oh, you're an American. Yeah. What are you doing here?" "Oh, I'm here to give a lecture on the Webb Space Telescope." And he went back. He says, "The Webb Telescope. I worked on the Webb Telescope too." And I said, "Oh, really? Well, what do you do?" And he said, "Well, my company makes machine tools, and I helped write a program for one of our machines that made a part for the telescope." And so he was just incredibly invested in this telescope for this part. And I went back, and I've been involved in the telescope since '99. I was one of the first half dozen or a dozen people that worked on. And I went back and I talked to the Lee Feinberg. I says, we get jaded and we don't seem to understand. We work with this thing. We live and eat, breathe, and sleep this thing every day. And maybe we get used to the idea that, this is just routine. But there are people out there that touch it just for the shortest period of time. And it doesn't matter how much you've done or how little you've done. Everybody's contributed. There's literally tens and tens of thousands of people around the planet that contributed to this mission. So anyway, now your question.
Yeah, exactly. This was exactly my point. I was trying to say I can appreciate how much work you guys have done in it. My question is mainly on the life side of things. You mentioned that you guys were looking into perhaps finding life or potential livable planets, right? I'm assuming this is mainly carbon-based life, right? Or were you guys considering other chemical-based? I know these are mostly theoretical and nobody has found anything on Earth that is not carbon-based, but just want to see if in theory that was even considered.
So the first thing is Webb's not going to be able to find habitable planets. That's not its mission. That's the mission of the next big one that was recommended. And the second thing I want to say is that mission is not going to find life. That mission is only going to assess habitability. And in that case, it's our definition of habitability is that we're going to be looking for Earth-like planets around sun-like stars that have atmospheres and sizes and that we would consider habitable for us. Because but when we're looking at Mars, for example, we're defined, life on Mars would be microbacteria, and we're also searching for life on Enceladus, the moon of Jupiter, and so how we define life would be, I think, any kind of biological, any kind of self-sustaining, replicating biological activity. But I think habitability is more defined from the context of our own sense of familiarity.
All right, excellent. Thank you.
Okay, thank you. Mr. Majid.
Oh, thank you, Reza. Yeah, it's just a cultural, then I just call everyone Mr. instead of going by the first name. But thank you very much, Dr. Stahl, for your amazing talks. I have a question, and it's my question. It's about all the photos which takes by James Webb or by the Hubble, most of them, or let's say all of them, had some kind of the artistic concept. So my question is that how much those artistic concepts are real? For example, I don't know, when they have something like a pillar of creation, it's very nice, it's very beautiful, but it seems that there are some kind of the artistic concept also, some kind of the arts behind those images, which could be maybe, you know, separate us from the reality or something which is in the real. Is it
Yeah,
correct
I
or
saw.
not?
Yeah, in fact, I attended a colloquium, an entire colloquium, where the guy at Space Telescope Institute talks about how they create the images. And basically, what they do is they spread the spectrum out and from the telescope and assign different wavelengths that we can see to each of those wavelengths. And so most of the interpretation, if you will, most of the artistic component is in selecting the colors. The spatial detail is the spatial detail. That doesn't need to be manipulated, but we do, we do not see light at 10 microns or 28 microns or a 15, so they have to reassign, they have to compress the colors scale into something that we can see visually. And so that's the biggest difference.
So if I'm going to rephrase it, so it means that the color coding is something which is come from the artist, but
Yes.
the image is real, but the color coding is something which grab our attention or give us some inspiration, something like that.
Right, correct.
Oh yeah, it's nice. Yeah.
And I'm not sure, but if they don't necessarily tweak the color coding maybe slightly different for different, in other words, when they bring in a young star in some of those images, they give them a color coded red. I think sometimes they may give a specific color coding to identify a specific feature. But again, a young star could be shrouded by a lot of dust, and therefore it could be very hot and warm. Whereas when other times when we're looking at a star that's clearing out a pocket in a nebulae and it's really, really hot, then they run it down into the blue range. And so there may be a little bit of playing around from an artistic standpoint of which colors they pick. But generally, they like to make, the shorter wavelengths, the hotter colors, and the longer wavelengths, the cooler.
Thank you.
Okay, so let me ask a question myself. I mean, you talked about the folding process and testing the telescope before they launch. On planet Earth, we have gravity, and the folding process might be a little different from when you unfold the telescope in the space. I mean, how do we make sure that the folding process is according to what happens in a lack of gravity environment or microgravity environment?
Yeah. So when we were doing that work in the clean room, I roll back to the movie. All right, getting close. And it is an issue. You have to worry about it. Come on. There we go. Too far. So what you want to notice is that when we're doing this one right here, what you can see is there's an offloader. See, there's a wire right there going up to a track, and there's a wire right there going up to a track. And so in this one here, there's wires going up to a track that you can see as we move it. And so we're actually holding up the structure and offloading some of the mass of the structure to compensate for the gravity. But at the same time, it's a real issue is that if you don't take into account the effect of gravity, you can have a problem of things don't work right. Is that friction affects how things work. And so it's a real design element you have to take into consideration. There have been experiments where they have tried to do booms in space, where they deployed the booms out on flat floors that were like air tables to give them a nice smooth motion. But then when they got up into space, they didn't deploy right. The cables didn't work right. There was problems with the friction. So um, but that was actually one of the reasons Northrop Grumman was selected as prime contractor. Is they're the prime contractor, they're the people that make the TDRS satellites, and so the deployment mechanisms that were used on Webb are very similar to the deployment mechanisms that are used on the antenna for the TDRS, and so there was confidence that they had a TRL level technology solution.
How much was the level of troubles with the sun, the solar shields? They're pretty thin, and perhaps folding and unfolding is extremely risky, and with gravity and without gravity and with friction and everything. So
Yeah, the sunshade cost a lot more than anyone expected, and caused a lot more schedule delays than anyone expected, and went through more design changes than anyone expected. It was a real challenge. We thought about trying to make subscale demonstrations and flying in space, but it was just deemed to be too expensive. But yeah, no, the sunshade was possibly the most difficult part of the entire mission, even though it looks like it's very simple.
yeah, it doesn't look really significant, but I heard a lot about how much trouble the NASA went through to make sure that it's working.
Yeah. Fortunately, it wasn't my problem.
Majid has a question about I believe.
This one. Yeah, my question is also, could those protect the telescope from the solar wind and any kind of the CME which happening in the sun, or no, it's just the radiation and the heat?
No, so they do block the solar wind, but then what happens is that ionized particles come flowing off of the edges of the sunshade, and so we had to do an analysis of that and had to look at possible charge accumulation on the telescope from the charged particles. The one thing that we also studied was what happens when a micrometeoroid hits them. And so micrometeoroids will impact the shades, they'll go through, and it sort of acts like a shotgun blast, is that one pellet then produces a spray of particles.
Okay, so it means that it's something ongoing right now. Let's say it's still under the test. Let's say in reality.
Yeah, I think I hopefully we won't have any problems with it. But I mean, it's fully deployed now and nothing's moving. So it's just a matter of lifetime expectancy.
And sorry to interrupt again. So the life expectancy for those shades is 5 years, or it's
well, no, I mean, so the requirement of the mission goal was 5 years, but we designed it from an engineering standpoint to try to go to 10 to 15. So everything that we did to the mission was based to the entire project was around the idea that we wanted it to last for 10 to 15 years. And what we are discovering is that everything out at Sun Earth L2 lasts a whole lot longer than you think. Even the things that we put out a long time ago are lasting a lot longer.
Now a follow up to your discussion, Majid. But L2 is technically a saddle point. That means
yes,
Webb needs actually some fuel to stay around it. Why didn't NASA
a few kilograms per year? It's a few kilograms of fuel per year, and we use it. We like that location because it's a saddle point. Is that trash doesn't accumulate there, garbage doesn't accumulate there, is that debris doesn't accumulate there. It's going to fall either into the sun or away from the sun. And so we have to expend fuel to keep it there, but things that don't have fuel won't stay there.
You addressed my next question. So that's the reason why they don't use L3 and L4, because it's
Right.
technically a
Yeah.
minimum point.
Yeah.
So
Yeah.
things just fall into it. Oh, so that prevents it. Okay. So thank you. Anyone else? Yes, you can ask question.
Yes, Dr. Stahl, thank you very much again. I apologize that my questions is still in engineering matters, which I picked up from your lecture. However, it's up to you if you want to answer it or not. The point is that you mentioned that the sum of the event horizon of the two black holes, you raised that matters, and it reminds me the theorem presented by Stephen Hawking, that he wanted to prove that the entropy is always positive toward the expanding the universe. So I like to know if did you find any proof or data from James Webb to prove that theorem, because I remember that he had a hard time to prove the theorem of such based on the thermodynamic. Thank you.
So again, back in my NASA feed, there's been some interesting work on black holes that have been talked about recently. And I'm struggling to try to remember what it is that, and it's not related to Webb. I think the missions that are mostly spending their time looking at black holes is the Chandra telescope. And I think that there was something, a Chandra press release recently about a black hole that had eaten one of a star close by, and at some point in the past, 2, 3, 4, 5 months ago, and that in the last week or so, that black hole then burped, and a whole bunch of material was ejected. And there was some linkage in that press release that referenced back to Hawking's, and how this experiment or data, how this data from Chandra X-ray telescope had somehow validated a Hawking's supposition. And so what I would suggest you do is go to the Chandra Telescope website and look at some of their press releases. And I think that you'll find something there that is talking about black holes. And if I have a vague memory of so again, NASA gives me this daily email of, couple dozen. It's basically just 4-sentence synopsis of the news article, to just enough to familiarize myself. So I have just enough information to possibly be raw, to be useful, and not enough information to actually probably be anything other than wrong. But I think that Chandra has some results that you can go look at.
Dr. Hanochi, if you have a question.
Yeah, actually, my next question is about the first part of your presentation about the engineering of this telescope. For each of those 18 mirrors of the telescope, I can imagine that we need at least 2 actuators for aligning them in the way that they focus on the receiver sensor. My question is, what technology for those actuators has been used in order to have such an accuracy? Because I can imagine that the motions are very, very tiny, and the actuators must be very accurate in terms of following, reaching to certain positions.
So there's actually 6 actuators. It's a hexapod.
All right.
And then there's another actuator in the middle of the mirror that can adjust its radius of curvature. And it's actually fairly routine, stepper motors and gear ratios, and but for space and for it's a custom. It's actually they're reusing an actuator motor that was developed for the Spitzer telescope that was designed to work at 4 Kelvin, and we're using them at 30 Kelvin. So that's it's a fairly mature kind of technology, and they have about a 10 micron step size. No, 10 nanometer step size. So it's a very small step. But then because of the relative stiffnesses of the mirror and things like that, and the displacement angles, so it's a fairly precise. It's moving things to a few nanometers. We can position the segments to a few nanometers with respect to each other.
Thank you.
Majid, if you have.
Yes, and my question is about the redshift and the spectroscopy, because one of the main, let's say, result or let's say data conclusion from the James Webb Space Telescope would be based on the spectroscopy. But many samples or many spectrum which we acquire is also affected by the different kind of the redshifts. It could causes some kind of the, let's say, errors in interpretation of the data. Am I right or not? Or do we have some kind of the calibrated, let's say, a spectrum, something too?
So there's all kinds of different kinds of questions, and so one of the things is that different mass distributions along your optical path can have an impact as well. And so you almost have to do an inverse tomographic kind of analysis. But the details of that are sort of beyond me.
No, okay. But it's happening. Am I right? Because sometimes when it's come to interpretation, we cannot
I think
directly.
I think it's something that people look at. People take that into, it's a known phenomenon, and people take it into account in their data analysis.
Oh, okay.
Yeah, getting a redshift properly and correctly, it's a very hard job, and there's a high chance actually to be wrong, and you have to analyze it. I mean, you need multi filters, a spectrum or a spectrum to find basically the redshift to the best of your uh, precision, but it's a very complicated process, and you're right. I mean, it is possible to get it wrong. Now, let me just ask myself one question about, if you remember, Hubble Space Telescope took a deep field image out of, it was a very interesting story behind it, that I guess the director of the Space Telescope Institute decided to focus on this part of the sky where there is nothing there, and then take a picture in opposite to everyone else basically request. Is it possible that in future maybe James Webb does something similar, something which maybe it's not really interesting, and then suddenly they discover something as amazing as the Hubble Deep Field?
I'm sure that the Webb will also look at a Hubble Deep Field. At the same, I'm sure that Hubble will look at, actually, I'm sure that Webb will look at the same Hubble Deep Field in order to get a comparison. But I also want to say here, I got to find the right figures. Boom, 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 boom.
I was hoping for something more risky, something which.
Well, but the thing is, I'm trying to find. Why can't I find what I'm looking for? Oh, that's because I'm looking in the wrong place. Here we go. All right. First off, this image was supposed to only be a single star. I mean, this was just an engineering unit image, and it was just supposed to be a single star. And we looked at it, and we found all this background stuff. So again, that was completely accidental. The other thing is that this first release image, that first release image of Webb is a deep field. That was deliberately done as a deep field. It's a different deep field than what was done for Hubble because the center of this thing has got a gravitational lens. There's a foreground massive galaxy there that you can see all the Einstein arcs of the gravitational lens. But they did this deliberately to see how far back they could go from a lensing standpoint. So that was their first attempt. And again, this image was taken with only 12 hours of data. So there's going to be more images, I'm sure, coming that are going to look much, much further back. And because this telescope is so sensitive, we're going to have to look for parts of the sky that don't have a lot of foreground objects in order to see what's really happening back in the beginning. So I have hopes that we're going to be, I have full expectation that our socks will be knocked off over and over and over again.
Yeah, I agree. I guess it already did a lot. But I'm hoping for something far more riskier, something similar to Hubble Deep Field when it was taken. It was an absolutely dark region, no comparison, just something hoping for something different.
The question is, where is such a place in the sky today?
There is none, apparently.
Yeah, I think that's the answer.
Now, I was thinking maybe the center of the Milky Way galaxy is somewhere which maybe nobody wants to look at it now with Webb. Do you think if there is any project now aiming at?
Roman is going to look at the center, I think. I think as part of the microlensing experiments on Roman, it's going to be studying the center of the galaxy over and over and over again. So for those of you that are listening that might not know, the idea is that, well, I got to think about is that use the center of the galaxy sort of as a gravitational lens, and then you look for exoplanets that pass behind the microlens and they get blips. It's kind of an odd technique, but I think if I remember correctly, they're going to cycle back to the center of the galaxy every so often. I'm not working Roman, but I was looking at it early on, and that was something I think I remember them discussing.
Yeah, the only problem with these transient phenomena is just happens only once. They need follow up, and there is no sometimes hope for follow up.
Yeah, there is no follow up. Yeah,
it's just one time discovery, if possible. Wonderful. I mean, is there any? Oh, there is still question, Majid.
I shouldn't ask. Okay, I don't want to take your time a lot, but I have a couple of questions. I go with the first one, and the last one I open it to know later, because my question is about the aesthetic concept when they are going to design mirrors or even the James Webb, because the shape of the James Webb, everything seems that it's not just the scientific, not just following up the scientific concept. It seems that there are some artistic and the aesthetic concept also behind the design. Am I right? Do they consider those aesthetic and the artistic concept when they're designing such kind of telescope, especially something like James Webb?
There's no artistic component to the Webb telescope. It's, every single detail was driven by engineering parameters. The shapes, you think that those mirrors are honeycomb in shape. They're not honeycomb in shape. They're slightly distorted because they're projected honeycomb onto a surface, and that when you project onto a surface, it distorts the shape. So there's actually 3 different prescriptions. There's an A, B, and C prescription, and each one of them each of those 3 has unique shape as they fit together. I cannot think of any decision that I made based upon, gee, that would look good. Everything is functional. The form of the telescope is driven by the function of the telescope.
Since we are on this topic, how far away are we to have a consortium of small telescopes like a robots or bots actually working together to form a big gigantic maybe mirror, but not together like James Webb? I mean, each one of these to be separated, and then they create a bigger angular resolution. How far do you think technologically are we from that point?
So people have been thinking about that for a long time. There were some ideas back in the early 2000s for something called a stellar imaging mission, whereby you had a whole bunch of, say, 1 meter or 2 meter class mirrors on spacecraft that reflected light down onto that flew in formation and reflected their light down into a beam combiner to do a large image. So people are thinking about that, but and the other thing is we're looking at is formation flying for interferometers, structurally connected interferometers, and free flying interferometers. But the next several missions that we're looking at are still sort of in the same mode of conventional telescopes with conventional apertures. So my guess is that we're maybe 20 years out before we try some sort of a formation flying experiment. Um, I would also speculate that maybe somebody like DARPA would be the first group to try some sort of a formation flying experiment, possibly. But yeah, no, it's people are thinking about it, but I don't think we're anywhere anywhere near being able to try it.
Okay, interesting.
The other thing we're thinking about is in space assembly, just taking up lots and lots of pieces of structure and building a big telescope in space. And potentially that's something that'll happen before we try free flying and formation flying.
Mhm.
But who knows? I don't know.
What about the moon as a station for telescopes?
So people have talked about that. Roger Angel had a NIAC study, NASA Innovative Advanced Concept Study, the idea of putting a liquid mirror in a crater at the South Pole. The Webb telescope actually started out as a lunar telescope study in the late 1980s. The problem with the moon is lunar dust and actually seismic. It's seismically active. Um, whenever a micrometeoroid hits the moon rings like a bell. So it's actually not a very good platform for doing astronomy. The other thing is you have a mass penalty. Is you can put 4 times more mass in orbit around the moon than you can actually put onto the surface of the moon.
Mm-hmm. Interesting.
It's because you have to take propellant to land. Yeah, it takes propellant. It takes mass to land mass onto the surface of the moon.
Yeah, it's true. It's true. Interesting. Any other questions? Yes, you have your hand raised. So.
Yes, thanks again. Following Aliriz's questions, I like to ask Dr. Solis, what is the physical nature of the mirrors, whether it's a convex or concave, and whether any relationship between the diameter of the mirrors with the depth of the field that can be seen? Thank you.
Yeah, so the optical prescription of the telescope is a 3-mirror anastigmatic design telescope. As compared to Hubble, Hubble is a Ritchie-Chrétien. So a Ritchie-Chrétien telescope is a concave parabola with a convex hyperbola down to the focal plane. And because of that, it has a fairly narrow field of view. But Webb is a 3 mirrors anastigmatic. It's a concave parabola, a convex hyperbola, and then it goes into a tertiary mirror. And because we have 3 mirrors, we have a bigger field of view. And so I'll show this. This is the thing here. So Hubble is the field of view of the telescope goes with the wavelength of the telescope. So, and the size of the mirror. So you see Spitzer is an 80 centimeter mirror. And because it's infrared, it's got a really large field of view with the 2-mirror telescope. Hubble, because it's in the visible and it's only a 2-mirror telescope, it's got and it's also 2-meter diameter, it has a much smaller field of view. If Webb was a 2-mirror telescope, it would have a really, really small field of view. because it's bigger. It goes from small aperture, large field of view, to large aperture should be small fielded. But because Webb has got 3 mirrors, it actually has a large donut shaped focal plane, which is what I showed up here, is that the focal plane of the Webb actually is a complete donut around the optical axis. And so we took a big piece of that and populated the instrumentation on it.
Interesting. Thank you.
Oh, Majid still has question.
Sorry, I know you are tired and I don't want to take your time. It's my last question.
I guess this would be the last question we ask.
Yes. Sorry, my question is not scientific question. It's maybe also scientific also. It's a general question. And I also, make it open to the floor to everyone. That what do you think about the impact of some project like James Webb on humanities and our daily and modern life? Do you think those kind of the project, if I'm going to ask, it's a personal also question, maybe not very scientific question, will have some effect in our humanity and modern life or daily life? If someone, let's say an ordinary guy or person passed and said, okay, what's the impact of such kind of project or such kind of project like James Webb on my life or people's life?
So an astronomer friend of mine liked to say that astronomy was the most important social fact, science, in that it completely changes political and the way humans look at, that before Copernicus, humans thought themselves to be the center of the universe and everything revolved around them. And as we do missions like Hubble and Webb, we see the vastness of the universe. And but I also want to say that it's my experience, everyone brings their own sets of experiences and biases and takes away from the data things that reinforce their own thought processes and thinking. In that the agnostic can look at this and marvel at the laws of physics and chemistry and quantum mechanics, and the religious look at this data and see the works of an almighty divine entity. And so I think different people take away different lessons, if you will, and different meaning. I don't want to say lessons. I'm struggling for the words, but I think everyone brings their own set of experiences to the data and takes away their own unique meaning. And most people, those meanings probably fall into broad buckets, but everybody's meaning is unique to themselves.
So
I guess I can add only one thing to it. The only thing which is universal is the sense of awe. Everyone will be, amazed by the beauty of the images we get from space. And regardless of whatever you interpret, nobody says it's ugly. Everyone agrees that it's beautiful, amazing.
So I actually ran into a person today. I actually ran into a person today who, when she found out that I'd worked on the Webb, when they discovered that I had worked on the Webb, they got kind of a little bit hostile, and they said, "Well, I just hope the whole thing falls flat on its face, and that we stop talking about this Big Bang nonsense." The world was created 13,000 years ago, and all of the science stuff is unimportant and irrelevant. So this person was finding a meaning for what they're finding in the data that is it was it was the first time I've gotten that reaction from someone. And I will also say I've met people on airplanes flying places that have thought that we never went to the moon. And I've met people, in stopping at burger joints in Los Angeles, that think that the world is flat. And
Yeah.
so it's yeah. But anyway, I chose not to engage this person, and I just listened to their rant and
So the good thing is that at least they went up from 6,000 to 13. We just have to wait a couple more centuries to get to 12 billion.
Yeah.
But the average is 10,000.
Yeah.
Yeah, but this is nice because I think it's those things, as Ali's also mentioned, and you could bring some kind of the meaning for us and some kind of the sense of awe. Yes, the sense of awe maybe is something which is could created maybe by some project like James Webb, because everyone will feel that we are a tiny creature in the world.
Yeah.
It's true. They may actually hate the conclusion that we make from every image and perhaps about the universe. But if you show them the image without any context, without any agenda, and you tell me something about this image, without exception, they all agree that it's something beautiful, colorful, amazing. But yes, it's true. Agendas and political agendas and religious agendas are always changing things. I mean, it's human perspective, so we have to acknowledge that.
Because I don't want to talk about that, because the first image, I think when it was released in front of the President Biden. Am I right? He was present.
Yes. Yeah.
So it means that it's very important also politically, and let's say something is important that they bring it to the president, show it to the president. Started from his presence.
Yes.
No, I think it's for anyone. It's politically very significant. It's like LHC. These are the greatest projects man can ever been able to achieve. I mean, it's not something that anyone can take credit for it, but at the same time, everyone on this planet can take credit for it. It's a humanity's achievement in science and technology. So I'm not surprised that the president went there and then wants to take credit for it.
So it's interesting is that I was recruited for about a year to join the project. I was first approached to work on this in '98, and I didn't actually start working on it in '99. It took me about a year to say yes. And what I ended up eventually telling myself, the reason is I decided that I would regret not working on the next great telescope program, is that if I did not take this job and do this job, I would regret it. And so that's one thing. The other thing is now then, as I was preparing to launch, I did a lot of media interviews, and they kept asking me about whether or not I was nervous or had any concerns. And the thing is, I didn't. I was 100% certain it was going to work. I had not a doubt in my mind that there was any possibility. I was 100% confident that the work that we had done on this telescope, it was going to work. I was maybe concerned about the rocket blowing up on launch, but I knew everything else was going to work just fine.
Yeah, that is amazing. Majid, do you have a question or?
No.
Okay, then. So let me just end this dialogue. Thank you very much again, Dr. Stahl. It was an amazing talk and amazing discussion. I hope we can see you more in future and work together as well. On behalf of our group, again, I would like to thank you again and have a great night. Thank you very much again.
Yeah.